This is Dr. Shankaraiah from Department of Physics. In today's presentation, I am going to discuss part B, which is on long answer questions on module 3, which is lasers and fiber optics. So the first question in question bank on module 3 is that illustrate the characteristics of lasers and highlight the phenomenon of lasing action required for the production of laser. So the characteristics of laser light, there are 4 characteristics: coherence, monochromaticity, directionality, and high intensity. So these are the 4 characteristics of laser light. So this is how it is. Laser light is different from normal tube light, which doesn't have all these 4 characteristics. So coherence is one of the unique properties of laser light. It arises from stimulated emission of radiation. So yeah, since a common stimulus triggers the emission events which provide the amplified light, the emitted photons have a definite phase relation to each other. So this coherence is described in terms of temporal and spatial. Spatial means in terms of x and temporal means in terms of time. Okay, so basically in coherence means the 2 photons that are emitted in stimulated emission. So suppose this is photon 1 and this is photon 2. These photons are going to be in coherence. That means that they are going to be in phase, in the same phase. So they will be in the same phase not only in time but also in space. So both in spatially and temporally they are in phase. Okay, when the 2 photons are in the same phase, we are going to say that they are in same phase or they are in coherence. Okay, monochromaticity. So a laser beam is more or less in single wavelengths. Okay, so monochromaticity is nothing but this laser light is going to have single wavelengths or single frequency. Okay, so the line width of laser is extremely small. Okay, so how do we find the monochromaticity of a laser beam? You can find the degree of monochromaticity using this formula xi, which is a degree of monochromaticity, will tell you about d lambda by lambda or d nu by nu. So d lambda by lambda, which is equal to d nu by nu. So okay, so this is degree of monochromaticity in wavelength, or you can calculate also in frequency. Monochromaticity means basically it's this laser light is going to have single frequency. Directionality means laser beam is highly directional because laser emits light only in one direction. And how do we calculate the directionality of laser light? We can calculate the divergence. Divergence is nothing but the spread of laser light. Okay, so how much spread of this laser light can be calculated using divergence. So divergence formula is here: R1 minus R2 by D1 minus D2, where D1, D2 are distances. D1, D2 are distances and R1, R2 are radii. Okay, so we are going to take a distance D1 and look at the radius of the laser beam, and we are going to take another distance D2 and look at the radius of the laser beam R2. Okay, so then we are going to take the fractional of this radius and distances to find out the divergence of this laser beam. How much spread is there in laser beam? Okay, so this in general the divergence will be in milliradians for a laser beam. High intensity of laser light. In a laser beam, lot of energy is concentrated in a small region. This concentration of energy exists both spatially and spectrally. Hence, there is enormous intensity for laser beam. Okay, because of the laser beam is narrow in width and a lot of energy is concentrated in small region. That is why you get high intensity of this laser beam. Okay, so that is to know what are the characteristics of laser beam. Then we are going to discuss about the phenomenon of lasing action. Okay, so lasing action. So this in the figure shows the active medium enclosed in an optical resonator and being excited by a pumping agent. Okay, so this is the optical experimental setup of the lasing action. Okay, the resulting laser action is shown in figure consists of the following steps. To get the laser beam as output, there are 5 steps to be followed. Okay, so the first step is pumping, second step is population inversion, spontaneous emission, amplification, and oscillations. So these are the 5 steps that occur inside this experimental setup, and we get the laser beam as output at the end of the 5th step. Okay, so yeah, so what are there in this experimental setup? For example, so this is the optical cavity. Okay, so optical cavity basically contains 2 mirrors. back mirror which is 100% reflecting and front mirror which is partially reflecting. There are two mirrors. In between these two mirrors you have active medium. Okay, so active medium is nothing but the host material plus active centers. We will discuss in detail what is this active medium. So active medium is a host material plus active centers. Okay, so host material plus active centers together called as active medium, and this active medium is connected to a pump so that we can supply energy to the atoms in the ground state. They get excited to the higher energy level, and then we will achieve population inversion, stimulated emission. Finally, we get the laser beam as the output. Okay, so basically to describe what is the experimental setup of this lasing action. Basically, in lasing action we have optical resonator that consists of two mirrors, front mirror and back mirror. Back mirror is 100% reflecting and front mirror is partially reflecting. In between these two mirrors, you have active medium connected to a pump. Okay. Yeah. So these are the 5 steps that occur in this optical resonator or optical cavity, and we will get the laser beam as output. Okay. So the primary function of optical resonator is to provide positive feedback of photons into the medium so that stimulated emission is sustained and the laser acts as a generator of light. Okay. So why do we need this optical resonator, or what is its function? So the primary function of this optical resonator is to provide positive feedback of photons into the medium so that stimulated emission is sustained. Once the photons are emitted from this active medium, whenever there is a photon emitted from this active medium, this photon is going to come to this mirror. This mirror is going to reflect. Okay, so if a photon goes backside, then the back mirror, which is 100% reflecting mirror, is also going to send the photons. So these optical resonator is going to basically provide the positive feedback of photons. That means that these mirrors are going to reflect the photons into the medium so that these photons are used to achieve stimulated emission, and hence once there is stimulated emission, we get coherent photons, and intensity will increase. We will get a laser light as a output. Okay, so the optical resonator selects the direction in which the light is to be amplified. So this is the primary function of the optical resonator. So coming to the first step in our lasing action is pumping. Okay, so atoms which are active centers in the medium are in the ground state. Okay, in the first, the atoms are in the ground state initially, as shown in figure here. You see all these atoms are in the ground state. Then by supplying energy from an external source using a pump, we have connected this active medium to a pump so that we can supply energy. Okay, once we supply energy from the external state, the atoms are excited from the ground level to an excited state. Okay, so this process is called pumping. By supplying energy to the atoms in the ground state, we are exciting the atoms from the ground state to the higher energy level so that population inversion is achieved. Okay, once we supply the energy to the atoms in the ground state, they are going to get excited, go to the excited state. And why the lifetime of atoms? So the second step is population inversion. The lifetime of atoms in the excited state is extremely small, of the order of 10 power minus 8 seconds or 10 power minus 9 seconds, for example. That is basically 1 nanosecond. So once the atoms excite from ground state to the higher energy level excited state, they are going to stay there for 1 nanosecond. After 1 nanosecond, they are going to come down to the ground state. Okay, so if you do not have a state in which atoms are going to stay for longer time, you are not going to achieve population inversion. So therefore the atoms drop spontaneously from the excited state to the metastable state in 1 nanosecond. Okay, as the lifetime of atoms at the metastable state is comparatively longer than the normal excited state, atoms are going to accumulate in the metastable state. As soon as the number of atoms in the metastable state exceed the number of atoms in the ground state, we are going to achieve this population inversion. So to achieve this population inversion, we need metastable state. Without metastable state, it is very difficult to achieve population inversion. If we have metastable state, the atoms that are excited to the metastable state are going to stay for longer time, and they are going to get accumulated in the metastable state. So the number of atoms in the metastable state are more compared to the number of atoms in the ground state. So that means N1 is greater than N2 is greater than N1. So this is N2 and this is N1. N2 is greater than N1 means we achieve population inversion. Once we achieve population inversion, some of the excited atoms of the metastable state may emit photons spontaneously. This is important. Once we achieve population inversion, some of the atoms in the metastable state, they are going to decay to the ground state through spontaneous emission emitting photon. Each spontaneous photon can trigger many stimulated transition along the direction of its propagation. Okay, these photons are going to come back into the system, and this photon is used as initial photon for this atom to get triggered by this photon to undergo stimulated emission. Okay, so yeah, so as the initial spontaneous photons are moving in different directions, the photons stimulated by them also travel in different directions. Many of such photons leave the medium without reinforcing their strength. The photons that are emitted in a direction other than the axial direction will pass through the sides of the medium and are lost forever. Okay. So once we achieve population inversion, the atoms in the metastable states are going to undergo spontaneous emission, and spontaneous photons that are going to be used as photons for the trigger the stimulated emission. And once we have stimulated emission, there will be coherent photons that are emitted. Fourth step, amplification. A majority of photons traveling along the axis cause stimulated emission and are reflected back on reaching the end of the mirror. They travel towards the opposite mirror, and they on their way stimulate more and more atoms and build up the photon strength. Okay, so now as the photons are, so we have active medium, right? So we have active medium in between the mirrors. This is one mirror and this one. We have two mirrors. So whenever photons are emitted, these photons are going to come back because of these mirrors. These photons are going to stimulate more and more photons. There will be stimulated emission, and more coherent photons are emitted. And because all these coherent photons are in coherence, they are going to be in the same phase, and hence once two photons are in phase, they will undergo constructive interference. Okay, because of the constructive interference, amplitude increases and intensity will also increases, because the relation between intensity and amplitude is I proportional to A square. A increases, that means intensity will also increase. Okay, so that is what is amplification. So the photons, the photons are then reflected again at the mirror and travel through the medium. As the photons reflected back and forth between the mirrors, stimulated emission sharply increases and the amplification of light takes place. The mirrors thus provide positive feedback of light into the medium, so that stimulated emission is sustained and medium operates as an oscillator. So final step is that at each reflection at the front end mirror, light is partially transmitted through it. So the transmitted component constitute a loss of energy from the resonator. When the losses at the mirrors and within the medium balance the gain, a steady and strong laser beam will emerge from the front end mirror. Okay, so that is how we get the laser beam after these 5 steps. Okay, so that is about this question. What are the 4 characteristics of lasers and phenomenon of lasing action? Explores the phenomena of absorption pumping mechanism related to the excitation of atoms from lower to higher energy state. Okay, so what is absorption and pumping? Okay, so absorption means if a photon of energy h nu collides with an atom present in the ground state of energy E1, then the atom completely absorbs the instant photon and makes transition to excited state E2. Okay, so now I have energy level E1, energy level E2. E1 is ground state and E2 is excited state. Atom is present in the ground state. I have given a photon. This is my initial or input photon. So this atom is going to absorb this photon and going to get excited to the higher energy level. So this is called absorption. Okay, atom in the ground state absorbs the photon completely and excite to the higher energy level. Pumping. It is defined as a technique to supply or provide energy to the atoms in the ground state so that they excite to the higher energy levels. As shown in figure A, we can supply energy in the form of light or in the form of electric field to excite atoms from ground state to the excited state, as we discussed. So pumping is the only process or technique in which we supply energy to the atoms in the ground state so that they get excited to the higher energy level. Okay, so you can draw the diagram and explain it neatly. Demonstrate the construction and working of a Ruby laser in detail with the help of a neat shootable diagram. So we need to discuss about Ruby laser with a neat diagram. So yeah, so this is the construction of Ruby laser. Okay. So and this is the energy level diagram. So let us see what is there in this. So Ruby laser belongs to the class of solid state laser. Ruby laser is a solid state laser. Ruby is basically Al2O3 crystal containing about 0.05% of chromium atoms. Chromium ions are actual active centers, and aluminum and oxygen are inert. So Al2O3, so we are this Ruby is going to have some 0.05% of chromium atoms, and these chromium atoms are the active centers, and aluminum and oxygen are inert. They are not going to participate in reaction. So Ruby rod is in the form of taken in the form of a cylindrical rod about 4 centimeters in length and 1 centimeter in diameter. Its ends are polished such that the end faces are exactly parallel and perpendicular to the axis of the rod. So we have taken here one cylindrical Ruby rod is in the form of cylindrical rod around 4 centimeters in length. So the length of this is 4 centimeter and the diameter is around 1 centimeter. Okay. So the ends of this Ruby rod are polished such that they are going to act as a optical resonator. We need optical resonator for to provide the positive feedback of atoms, right? Yeah. So the end faces are silvered such that they form optical resonator, and rear face is made totally reflecting while the front face is partially reflecting. So that is how we create this optical resonator. The laser rod is surrounded by helical photographic flash lamp filled with xenon. So this is the xenon flash lamp, right? So this is the xenon flash lamp. This xenon flash lamp is connected to the battery and power supply. We can change the voltage and supply power to this xenon flash lamp. So whenever activated by the power supply, the lamp produces flashes of white light. Okay, so whenever we switch on the power, this xenon flash lamp is going to give us flashes of white light. And these are the energy levels of chromium ions in the crystal lattice shown in figure. The energy level structure of chromium ions is characterized by 2 absorption bands. So this one, these two are the absorption bands and 1 metastable state. So E2 is a metastable state, E1 is a ground state. So E1 is ground state, E2 is metastable state. E3 and E3 prime are absorption band and normal excited states. Okay. So pumping mechanism. Okay. So when the xenon flash lamp is switched on, the discharge generates an intense burst of white light lasting for a few seconds. Chromium ions are excited to the energy bands E3 and E3 prime by the green and blue components of white light. The chromium ions undergo non-radiative transitions from these energy level to E2, and E2 is a metastable state. So metastable state E2 has a lifetime approximately 1000 times more than the lifetime of E3 and E3 prime. So therefore chromium atoms accumulate in E2 level. So there will be population inversion between E2 and E1. So E2 is the upper laser level and E1 is the lower laser level. Between E2 and E1 we get population inversion. So population inversion is between E2 and E1. So lasing action. So a chance photon is produced when a chromium ion makes a spontaneous transition from E2 to E1. So this spontaneous photon stimulates another excited ion down to a downward transition. So this stimulated photon and initial photon trigger many excited ions to undergo stimulated emission. So whenever there are stimulated photons or coherent photons that are produced, these photons are in phase and they are going to undergo constructive interference, and we are going to see there are red photons of wavelength 6943 angstroms traveling along the axis of the Ruby rod, repeatedly reflected at the mirrors, and light amplification takes place. So on attaining sufficient energy, the laser beam emerges out through the partially reflecting mirror. The laser emission occurs in the visible region at a wavelength of 6943 angstroms. Once stimulated emission transition commences, the metastable state gets depopulated very rapidly and the state of population inversion disappears and lasing action ceases. So the laser becomes active once again when the population inversion is re-established. So therefore the output of the laser is not a continuous wave but occurs in the form of pulses of microsecond duration. So in Ruby laser, whatever output we are getting, that laser is not a continuous wave, it is pulses of microsecond duration. So these are some salient features of ruby laser, which uses 3-level pumping scheme. Chromium atoms are the active centers. Xenon flash lamp is the pumping agent, operates in pulse mode. Narrate the construction and working of helium neon laser in detail with the help of neat diagram. So we have discussed now ruby laser. So this is about helium neon laser. Okay. So gas lasers are mostly used, widely used lasers, and they range from low power helium neon laser in college laboratories to very high power carbon dioxide laser in industrial applications. Gas lasers are actually used most widely, and these lasers operate with rarefied gases and as an active medium and excited by this electric discharge. So here we are not going to excite the atoms from ground state to higher energy level by light. We need to use electric discharge because the energy levels of atoms involved in lasing process are very narrow, and as such require sources with sharp wavelength to excite ion. So because of this sharp wavelength, we are going to use electric discharge instead of light as the pumping agent in helium neon laser. So the first gas laser was helium neon laser, which was invented in 1961 by Jaban, Bennett and Harriot. Okay, so this is the construction of helium neon laser. Helium neon laser constitutes a long discharge tube filled with mixture of helium and neon gases in the ratio of 10:1. So for each 10 atoms of helium, there is only 1 atom of neon. Okay, so this is the long discharge tube. You have long discharge tube, and this tube is connected to electrodes. Okay, and this tube is filled with gas mixtures, helium and neon. Helium atoms are 10, and there should be 1 neon atoms. Okay, so neon atoms are the active centers and have energy levels suitable for laser transitions, while helium atoms are helping these neon atoms for this for population, to achieve population inversions. Electrodes are provided in the discharge tube to provide discharge in the gas. They are connected to the high voltage power supply. The tube is hermetically sealed by the inclined window, so there are this tube is tightly sealed so that there is no leakage of gases. On the axis of the tube, the 2 mirrors are arranged externally, which form the Fabry-Perot mirror. So there is 1 mirror and there is 1 mirror. So there are 2 mirrors to form the optical resonator for the positive feedback of photons. So how does this work and how do we get laser beam? Okay, so these are the energy levels of helium. So you have F1, F2. Helium atoms have 2 energy level. F1 is ground state and F2 is metastable state. Whereas neon has E1, E2, E3, E4 and E5. So out of these, E2 and E3 are metastable states, and E5, E4 are normal excited state, and E1 is the ground state. Okay. Yeah. So when the power is switched on, a high voltage of 10 kilovolts is applied across the gas mixture. It ionizes the gas. The electrons and ion produced in the gas. So here, whenever the power supply is on, we are going to produce the electric discharge. There is going to be ionization of the gas. Electrons and ions produced. That means electrons, whenever the atom loses its electron, it is going to be a positive ion. So there will be electrons and ions in the gas mixture. They are going to accelerate towards the anode and cathode respectively, because there are positive ions and negative ions. They are going to go to the respective cathode and anode, and they collide with the helium and neon atoms on the way. Out of these helium and neon atoms are the lighter ones, so they are going to get excited first. One of the excited levels of helium is F2, that is this. This is helium atom energy levels. Okay. So the energy of this helium atom energy level F2 is 20.61 electron volts above the ground level. So this is ground and this is the excited state, metastable state, which is 20.61 electron volts energy. It is a metastable state, and the excited helium cannot return to the ground level through spontaneous emission. Okay, so it is going to lose energy, transfer some of its energy to the neon atoms. Okay. So the excited helium atom can return to the ground state by transferring its excess energy to a neon through collision. Okay, such energy transfer can take place only when 2 colliding atoms have identical energy levels. Such transfer is called resonant energy transfer. Because F2 is a metastable state, this helium atom is not going to return to the ground state through spontaneous emission. It has excess energy. So this excess energy can be transferred to the neon atom by collision. Okay. So this is possible only when the two atoms have identical energy level. For example, helium has F2, which is around 20.61 electron volts, and neon is also having energy level E5, which is 20.66 electron volts. Okay. So now this helium atom is going to transfer its energy to the neon atom, and the excess energy of 0.05 is going to come to the neon atom through kinetic energy of the helium. Okay, so that is how this helium atom is going to transfer energy to the neon atom, and that is possible only when the two atoms have identical energy level, and such energy transfer is called as resonant energy transfer. So by transferring energy to the neon atoms, helium atoms are going to decay to the ground state. Okay, so therefore resonant transfer of energy occurs between the excited helium and the ground level neon atom. The kinetic energy of the helium atoms provides additional energy of 0.05 electron volts required for excitation of the neon atoms. So helium atoms are in the metastable state. So helium atoms transfer their energy to the neon atoms in the ground state. Okay. So neon atoms are basically in the ground state. So they transfer their energy to the neon atoms, and they will decay to the ground state. Now the neon atoms absorb the energy of 20.66, 20.01 from 20.61 from helium atom. The additional 0.05 electron volts comes from the kinetic energy of helium, and that is how it gets the total energy of 20.66 electron volts to excite to the higher energy level E5. So helium atoms drops to the ground state after exciting the neon atoms. So this is the pumping mechanism in helium neon laser. So the upper state of neon atom E5 is a metastable state. So here E5 is a metastable state. Okay, so E5 is a metastable state and E2 is a metastable state. Therefore, neon atom accumulate in this upper state. E3 level is sparsely populated at ordinary temperatures. So population inversion achieves between E5 and E3. Okay. So this is where, so you have E5 and you have E3. So between these two energy levels, we achieve population inversion, and there will be, once there is population inversion, we will have spontaneous emission. One of the atoms are undergoing spontaneous emission, and then that photon is used to trigger the neon atoms to undergo stimulated emission. And once there is stimulated emission, that they are going to emit photons, coherent photons, and which is wavelength around 6,328 angstroms, which are in color red. The transition between E5 E3 generates a laser beam of wavelength 6,328 angstroms. From the level E3, the neon atoms drop to E2 spontaneously. E2 is also again metastable state. So consequently, neon atoms tend to accumulate in E2 level. Neon atoms return to the ground state E1 through frequent collisions with the walls of the glass tube. That is why we take the glass tube purposefully as narrow, very narrow, so that once the atoms come to the ground metastable state E2, they are going to collide with the walls and they are going to decay to the ground state through collisions. The neon atoms are once again available for the excitation to the higher energy state and participate in lasing action. So the neon atoms are excited to the upper lasing level continuously through collisions. Population inversion is maintained in the face of continuous laser emission. The laser operates in continuous mode. So in helium neon laser, we use a 4-level pumping scheme. Active centers are neon atoms. Electric discharge is the pumping agent, and it operates in continuous wave mode. Fifth question. Enlist the importance of lasers in the fields of industry, medicine, science, etc. by giving their applications. Okay. So we use lasers in various fields. For example, in communication, we use in communication. For example, in telecommunication, we use lasers are used to light source to transmit audio, video signals and data to long distances without attenuation and distortion. Okay, and we also use these lasers for underwater communication because so we use in underwater communication. Industrial application we use for metal cutting and drilling, welding, surface treatment. Okay, so in ICs, trimming the components of ICs. in industrial application also we use these lasers. Medical applications, for example, improve precision work like surgery. Brain surgery is an example of precision surgery. Okay, so we also use in cosmetic surgery, dermatology, eye surgeries, laser surgery, soft tissue surgery, dental problems. So there are many applications in medical field. Military applications, we use lasers at depth rays as a laser gun, as lidar. In computer also we use to read and write the data. We use in thermonuclear fusion in scientific research in various. These are some of the fields where we use lasers. Sixth question: discuss in detail the phenomenon of spontaneous emission and stimulated emission. Okay. In lasers, the interaction between matter and light is of three different types: absorption, spontaneous emission, and stimulated emission. Okay, to understand this spontaneous and stimulated emission, I am considering two energy levels of an atom. So I have considered an atom. This atom has two energy levels, E1 and E2. Okay, so atom is now in the ground state. This is the atom, it is in the ground state. Okay, so I'm going to supply energy in the form of photon. So photon means light. So okay, so this atom which is in the ground state is going to get absorb this photon and get excited to the higher energy level. So that is called absorption. So as we discussed earlier, see, so this is absorption. The atom in the ground state absorb this photon and get excited to the higher energy level by absorbing photon completely. Absorption. Spontaneous emission. Now atom is in the excited state E2. Okay, so atom is going to decay to the ground state spontaneously or voluntarily by emitting a photon. Okay, so this is called spontaneous emission. Okay, and the photons that are emitted in spontaneous emission are incoherent, so they are not going to be in the same phase. Stimulated emission, for this, even in the stimulated emission, the atom is in the excited state. Now we are going to supply photon. Okay, so this photon is going to trigger the atom. This photon is not absorbed by the atom. Okay, it is just going to trigger the atom to undergo stimulated emission. So this atom that decays to the ground state is going to emit another photon, and the initial photon and the emitted photons are in the same phase. So they are coherent photons. So in stimulated emission we get coherent photons, whereas in spontaneous emission we get incoherent photons. That is the difference. What do you mean by population inversion? Explain it using 3-level diagram. Also discuss why population inversion is essential for laser action. So population inversion condition on the population distribution between energy levels E1 and E2 is inverted, and hence is known as inverted state. This is also a non-equilibrium. So population inversion condition is also called as inverted state or non-equilibrium state, and it exists only for a short time. Okay, it is needed to achieve stimulated emission. To achieve stimulated emission, we need this population inversion. Okay. So how do we achieve this population inversion? We achieve population inversion by using various pumping technique. Okay, so yeah, yes, so we can achieve this population inversion using pumping techniques. Basically, you can use. We can discuss about this. We can discuss about Ruby laser. We can consider this 3 energy level diagram, right? So three energy level diagram. So we achieve population inversion E1, E2 and E3, for example. Okay. So discuss this 3 level diagram. Okay. So we have discussed the application. Now, yes. So we are going to use 3 energy level diagram E1, E2, E3, for example. So E1, E2 and E3. So E3 is a normal excited state. So this is not metastable state, normal excited state, but E2 is a metastable state, for example, and E1 is a ground state. Okay, whenever we supply energy to the atoms in the ground state, these atoms are going to get excited to the higher energy level E3 first. We are going to supply energy necessary, whatever energy needed for the atoms to excite E3, we are supplying energy in the form of photons. These atoms are going to get excited to the higher energy level E3 first by absorbing the photons. Now, once the atoms excited to the higher energy level E3 is a normal state, excited state. So in normal excited state, the lifetime is 1 nanosecond. So immediately these atoms, so now actually, okay, so this is the first step. Once they excite to the higher energy level, they are, all of them are going to be in the excited state. Okay, so E3, E2 and E1. Okay, now because the lifetime is very small in normal excited state, they are going to decay to the metastable state E2. E2 is a metastable state. So the lifetime is more here. So 1000 times more than the normal excited state. So there will be more atoms. So this is the next level. So there will be more atoms in E2 compared to E1. So that is how we achieve population inversion between E1 and E2. E2 is called upper lasing level and E1 is called lower lasing level. Okay. So basically this population inversion is achieved using pumping techniques, and once we have population inversion, we are going to have stimulated emission, and hence we are going to get coherent photons. These coherent photons are going to get amplified to give us laser beam. So we need this metastable state and population inversion to achieve to get this lasing action. Okay. So metastable state, there could be no population inversion and no laser action if metastable state do not exist. If there is no metastable state, we are not going to get any population inversion. If there is no population inversion, we are not going to get any laser beam as output. So we can take laser, ruby laser and helium neon laser as to explain how do we achieve population inversion and how lasing action takes place. Okay, we can take one of them. So we have taken here ruby laser. So illustrate the purpose of an active medium and optical resonator in a laser system. So what is the active medium and how is it useful in a lasing action? So this is the active, so this is the optical resonator in which you have optical resonator, you have two mirrors partially reflecting and 100% reflecting. In between you have active medium that is connected to a pump. Okay. So the active medium is a material in which laser action takes place. The most important requirement for the laser medium is that we should be able to achieve population inversion in this medium. Only a small fraction of atoms of a particular type have energy level system suitable for achieving population inversion. Such atoms can produce more stimulated emission than spontaneous emission and cause amplification of light. These atoms which cause lasing action are called active centers, and the rest of the medium acts as host and supports the active centers. So the medium hosting active centers is called active medium. So active medium is nothing but the medium which host the active centers. So if we do not have active centers, there is no population inversion. We do not get any laser light. Okay. So we need active centers, and these active centers are hosted by this active medium. So active medium is a medium in which when excited reaches the state of population inversion, promotes the stimulated emissions leading light amplification. So this is active medium is a medium in which we are going to get this light amplification because it promotes the stimulated emission. The primary function of optical resonator is to provide positive feedback of photons into the medium so that stimulated emission is sustained and the laser acts as a generator of light. Ninth question. How light amplification is achieved in a laser system? Okay, so again we discuss about the lasing action. So starting with the diagram, need diagram, and then we will discuss about these 5 steps that are involved to get this lasing action. Explain the pumping process involved in laser emission. Also discuss in detail different pumping mechanisms. Okay, so we know what is pumping. Pumping is basically a technique to supply or provide energy to atoms in the ground state so that they get excited to the higher energy levels. Okay, so we can supply energy in the form of light or electric discharge. So in the ruby laser we have used light, xenon flash lamp as the pumping agent. Okay, so in the case of helium neon laser we have used the electric discharge as a pumping agent. Okay, to achieve this population inversion and stimulated emission. Finally we got the laser beam as output in these 2 lasers. So that's how we explain pumping process and different pumping mechanisms. Light, laser beam, light, xenon flash lamp as a pumping agent in ruby laser, and electric discharge as a pumping agent in helium neon laser. So you can explain in detail about this. These are some of the textbook used and references used for this presentation. To summarize, in this presentation I have discussed about question bank on module 3, which is lasers and fiber optics. So I have discussed the long answer questions, which is part B. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.